The third interstellar object ever discovered should have been ordinary, a silent wanderer of ice and dust reflecting sunlight like every comet before it. But this one, cataloged as 3I Atlas and soon nicknamed 3I Atlas, broke every rule of physics that astronomers thought they understood. It didn't shine like a comet should dot a globe, not from behind, but from the front, a steady, forward-facing brilliance that refused to obey the laws of reflected light. When the first composite images came back from Hubble and JWST, researchers expected the familiar comet profile, a faint nucleus surrounded by a halo of gas, streaming outward into a tail as sunlight vaporized surface ice. Instead, what they saw looked wrong. Atlas seemed to defy the sun itself, the brightest part of its coma. That misty sphere of gas and dust surrounding the body wasn't trailing behind. It was facing forward, directly into the solar wind, glowing as though lit from within, and the data didn't lie. The dust around it was too thin, the core too small, and yet the brightness rivaled objects twice, even 3 times its size. Astronomers ran the math over and over, hoping for a calibration error or a trick of perspective. But no, every frame confirmed the impossible. Some, like the ever-provocative Avi Loeb, began to whisper the unthinkable. What if Atlas isn't reflecting sunlight at all? What if it's producing its own light, a nuclear heart burning in the dark? If Loeb was right, the discovery would rewrite not just cometary physics, but the entire history of interstellar matter. Either Atlas was something entirely new, or humanity had just stumbled upon technology far older than civilization itself. The first close-up analysis from Hubble told an unsettling story. The team expected to see sunlight reflecting most brightly from the rear of the nucleus, where vaporized dust clouds are thickest. Instead, brightness peaked on the sunward side, and the glow dropped sharply behind it. This wasn't how sunlight worked. To confirm, imaging teams plotted the surface brightness profile, a map of intensity across the object's face. The result was a glaring asymmetry. The brightest region sat ahead of the nucleus, not behind it. They calculated the phase angle, the geometric relationship between the sun, the object, and the observer, and ran light scattering models to test whether forward reflection could explain the anomaly. But even under the most favorable geometry, the numbers broke down. The coma's optical depth, a measure of how dense and reflective the dust cloud is, was far too low. The material was optically thin, meaning sunlight should have passed through it rather than bouncing forward with such intensity. To match the observed glow, the coma would need to be thousands of times denser or the nucleus vastly larger than the data allowed, but Hubble's sharp eyes saw no such nucleus. There was no brilliant point source, no dense reflective rock hidden inside the haze, just that eerie, forward-facing glow, unwavering and real. Teams rechecked their instruments. They recalibrated sensors, compared exposures, tracked the object across multiple nights and multiple observatories. Yet the results stayed stubbornly the same. This wasn't an illusion. Something inside Atlas was shining. If sunlight couldn't explain it, the power had to come from within. Astronomers crunched the luminosity equations. For the observed brightness to be natural, pure reflection, Atlas would need to be roughly 20 kilometers wide, a massive object easily visible as a solid point in every Hubble frame. But it wasn't. Data from both Hubble and Palomar Observatory told the same story. The nucleus was small, painfully small, less than 4.4 kilometers in radius, perhaps even closer to 0.8. The coma itself, though expansive, was ghostly thin, not enough dust to act as a mirror, not enough particles to scatter sunlight effectively. Even when astronomers tweaked their assumptions, making the dust darker, brighter, coarser, smoother, the math refused to budge. There simply wasn't enough matter to justify the light pouring from Atlas's head. Too little dust, too small a body, too much light. That became the unofficial model whispered in labs across the world. The standard Comet model was cracking, and when that happens in science, something extraordinary is often hiding behind the fracture. Was this a natural body harboring an unknown energy source? Or had something, or someone, built it? Then came the next anomaly, the orbit. 3I Atlas didn't dive into the solar system from above or below, like most interstellar visitors that slice across our planetary plane at sharp, random angles. Instead, it skimmed almost flat, just 5 degrees off the ecliptic, the very same plane where all major planets revolve. Even more strangely, it moved retrograde, against the flow of every world orbiting the sun. Statisticians at multiple observatories ran probability models, The odds of an interstellar object arriving with this kind of near-perfect ecliptic alignment purely by chance were 1 in 500. That's not impossible, but it's highly unnatural. The ecliptic, after all, is a thin, delicate slice in an ocean of three-dimensional space. For Atlas to align so closely meant either staggering coincidence or intent. Its path wasn't chaotic or random. It was methodical, threading a route past Venus, Mars, and Jupiter, the main planets used for gravitational assists in spacecraft missions. And as one astrophysicist quietly put it in a conference hallway, it's flying the same highway we use, almost as if it were alive. That was the phrase whispered in control rooms and mission briefings as the orbit of 3I. Atlas was refined. The object wasn't tumbling randomly through the void, nor was it plunging recklessly toward the sun. Instead, its trajectory unfolded like a carefully plotted tour of the inner solar system, a smooth, calculated arc that brushed past the orbits of Venus, Mars, and Jupiter, each encounter close enough to be deliberate, almost like it was sampling the system's main attractions. Space doesn't do symmetry. Not naturally. Randomness rules everything beyond our sky: comets, asteroids, rogue interstellar wanderers, all drifting with chaotic inclinations and eccentric paths. But Atlas was different. Every calculation, every simulation brought researchers back to the same razor-thin line, the ecliptic plane. It was the cosmic highway, the same narrow corridor along which Earth, Mars, and the rest of the planets travel. The same path humanity uses when launching probes from one world to another. In a universe of infinite directions, Atlas had chosen ours. Mars would be the first to witness its close approach on October 3rd. The interstellar visitor would sweep past the red planet at a distance of just 0.19 astronomical units, roughly 28 million kilometers. For cosmic terms, that's practically a handshake. It would be the closest approach to any major planet during its entire run through the inner solar system. For a brief, precious few hours, Mars-based orbiters, Maven, Mars Express, Hope, and the aging but persistent Odyssey would have a clear, unobstructed view. Scientists raced to schedule their instruments, hoping to catch the globe before the sun swallowed the object in its glare. By October 4th, Earth's telescopes would already be losing sight of it. By October 21st, the elongation angle, the apparent separation between Atlas and the sun, would drop to just 0.6 degrees. At that point, it would vanish completely, drowned in solar haze, invisible to every ground-based eye. Its perihelion, the closest point to the sun, would come on October 29th, a mere 1.36 astronomical units away. But not a single telescope on Earth would see it. The object would spend those crucial days behind the sun, hidden, silent, UNOBSERVABLE. By early November, it would re-emerge from the glare, already outbound, dimming, and racing away from the sun at over 150,000 miles per hour. Intercepting it was a logistical nightmare. Mission planners and propulsion engineers ran the numbers to catch up from Earth. A spacecraft would need a delta V of at least 24 kilometers per second, an impossible speed for any chemical rocket. Even the fastest interplanetary probes in history, like Parker's solar probe, couldn't reach it in time. Some proposed launching from Mars itself, exploiting the planet's weaker gravity and favorable position. That could cut the velocity requirement down to around 5 kilometers per second, barely within the reach of next-generation propulsion. But even that window was closing fast. There was one final, desperate idea. If the Juno spacecraft at Jupiter could execute a perfectly timed burn, it might swing close enough to intercept Atlas as it passed the giant planet's orbit. But even under ideal conditions, the probe could only come within 27 million kilometers, far too distant for any detailed study. Every hour that passed widened the gap. Every delay turned the opportunity into a memory. Atlas, it seemed, was designed to be unreachable. When the light spectrographs came in, they deepened the mystery instead of solving it. The reflected signal, faint but precise, split into a spectral fingerprint that revealed its composition: water, ice, silicates, carbon compounds, and complex organics. These were the ancient ingredients of the universe, the same materials found in the oldest meteorites and pre-solar grains. But there was something uncanny about the match. The closest known analog was the Tajas Lake meteorite, a rare carbonaceous rock that fell to Earth in 2000. One of the most primitive materials ever discovered. That same combination of organic dust and microscopic water ice grains appeared on Atlas, perfectly preserved, as if frozen long before our sun even existed. That, alone would make it a priceless time capsule. But Atlas's behavior told another story, one that didn't fit the quiet dignity of an ancient rock drifting through space. Hubble's high-resolution images showed faint dust streaming from its sunlit hemisphere, as expected, but the rate was shockingly low. At most, Atlas was shedding between 12 and 120 kilograms of material per second, a feather-light trickle compared to the violent jets and plume seen from typical comets nearing the sun. Over 6 months, that erosion would remove only a few centimeters from its surface, barely a scratch in cosmic terms. Some ground-based observatories came back with even smaller estimates, 1 kilogram per second. If that meant one thing: Atlas's crust was hard, ancient, and stable, not soft and eroding like normal comet ice. It wasn't sublimating away. It was holding together, resisting the sun's heat as though something inside it refused to let go. Thermal models ran the numbers again. The surface temperature was warm, but not dangerously so. No sudden flares, no geysers of gas, no outbursts. Just a steady, silent haze surrounding a compact, glowing core. The energy budget didn't make sense. If sunlight was the only source of power, Atlas should have been cold and dim. If it was a normal comet, it should have been losing mass, bursting with jets of vaporized ice. But it wasn't. It was calm, and warm enough to radiate light without burning away. Something was heating it from within. At Harvard, astrophysicist Avi Loeb stared at the numbers and offered the theory that made headlines around the world. "This isn't a dying comet," he said. "It's a working reactor." To most scientists, that sounded insane, but the math didn't laugh. The comet's persistent forward glow, the steady luminosity, the lack of dust density, the low sublimation rate, all of it pointed to one conclusion: there was an internal power source. Loeb proposed that Atlas might be harboring a nuclear heat engine, a compact reactor generating 10 gigawatts of power, radiating through the crust and lighting the coma from within. That wasn't just a metaphor, it was a direct calculation, the exact energy required to produce the observed glow, without relying on sunlight or outgassing. If true, Atlas wasn't just an interstellar object. It was something built. Loeb's calculations pointed to an almost unthinkable hypothesis: a steady 10-gigawatt internal power source, enough to light a major city, hidden beneath an ancient shell of dust and rock. That wasn't metaphor. That was energy, measurable, consistent, impossible. The coma around 3I Atlas glowed with a steady brilliance, completely unaffected by distance from the sun. Every comet in history brightens as it nears perihelion, then fades as it drifts away. This one didn't care. The glow was constant, as if the light wasn't reflected, but emitted. What if? Loeb asked in a paper that sent quiet shockwaves through the astronomical community. What if we're not seeing a dying comet, but a functioning machine? His model was specific. If 3I Atlas were powered by an internal reactor, perhaps a self-sustaining nuclear or fusion core, the brightness should remain constant throughout its journey. And it did. 6 months of Hubble and JWST tracking showed no variation beyond the margin of error. Spectral readings confirmed the dust was thin to scatter enough sunlight. The nucleus, estimated between 4 and 11 kilometers, was far too small to reflect the light levels observed. Even stranger, the object's surface loss over that period was measured at less than 1 millimeter. No natural comet could do that. By late 2025, the data was undeniable. A body the size of a mountain, older than the sun, following a path almost identical to human spacecraft, radiating 10 billion watts of energy from within, and showing no signs of decay. Its route carried it past Venus, Mars, and Jupiter, like it was observing, sampling, watching. When it vanished behind the sun on October 29th, every observatory on Earth turned their instruments toward the empty sky, waiting for it to reappear. Some said it was coincidence, an interstellar relic shaped by physics and chance. Others whispered something far more haunting: that 3I Atlas was built, a machine older than humanity, drifting through our system not by accident, but by design. And as it accelerated into the black, one truth remained: we were no longer alone in the void.